So let me just give you a quick recap of crystal field theory, what we were discussing. So in crystal field theory, in crystal field theory, what we were doing is that we said that when we have a metal ion and certain ligands approach this metal ion to form coordination bond with this metal ion. For example, they're trying to form a octahedral complex. So they exert a octahedral field around this metal ion, and in this octahedral field, what really happens is that the energy level of d orbitals does not remain same, and it actually becomes different, right? For example, I have 5 d orbitals which have same energy. Let's suppose dxy, dyz, dxz, dx2y2, and dz2, right? So these are 5d orbitals which we have. In ground state they have same energy, and that's why they're called degenerate orbitals, right? But the moment we try to form bond with 6 ligands through an octahedral geometry or through an octahedral field, so in the presence of octahedral field of 6 ligands, these two set of orbitals, these 5 orbitals gets divided into 2 sets. One set is called, what is it called? EG. Another set is called T2G. So the T2G contains dxy, dyz, and dxz, and EG consists of dx2y2 and dz2. So this splitting of energy of orbitals happens, and there is an energy gap which is created, which is represented by delta. So we use delta O or delta OCT octahedral. So O represents for octahedral geometry, or you can say that octahedral field. So in the presence of octahedral field, this kind of splitting happens. Energy of all the 5d orbitals will increase, but will not increase homogeneously. Increase in energy of 3 orbitals will happen in this way, and for the other 2 it will happen in this way, right? Now this is what we studied, and because of which we also studied that low spin and high spin complexes, how low spin and high spin complex concept works, right? So I'll continue with this point, and we'll start focusing on the crystal field theory in case of other complexes. Crystal field theory in octahedral complexes. Right? So in octahedral complexes, if I have 5d orbitals of equal energy, let's suppose this is the energy diagram which we have. This is dxy, dyz, dxz, dx2y2, and dz2. So in the presence of octahedral field, these 5d orbitals will not remain degenerate. They will split into 2 groups. One group is called EG and another group is called T2G, as we just studied initially, right? But if you remember, instead of drawing this diagram, actually I drew the other kind of diagram, in which what I said that if we exert a spherical symmetric field around these 5d orbitals, energy of all the 5d orbitals will increase, but will increase equally, which means that they'll still remain degenerate. This is in the case of spherically symmetric field. So energy of all the 5d orbitals will increase, but will remain same. Now but in the presence of octahedral field, this energy will not remain same and will get divided into 2 situations. One set is called T2G, another set is called EG, right? and this consists of dxy, dyz and dxz. This consists of dx2, y2 and dz2, right? This is happening in presence of octahedral symmetric field, right? So ये octahedral symmetric field में हो रहा है. So in this case, so they get split into two cases. One is EG, another is T2G. So in EG, E refers to the doubly degenerate. And in T2G, T refers for triply degenerate. So degeneracy means having same energy. So T2G means all three have same energy. EG stands for that they are doubly degenerate. So in which only E refers to the doubly degenerate and only T refers to triply degenerate, not EG or T2G. So this G and T2G refers to the molecular symmetry, and precisely here it refers to the orbital symmetry. So G stands for Gerard, which means even. So these terminology of EG and T2G refers to doubly degenerate orbitals which have some kind of symmetry, and again T2G also stands for some kind of triply degenerate orbitals which have some sort of orbital symmetry, right? Is this clear? Now, another thing which we discussed that day was that energy gap between the two is delta O. This delta O is called CFSE, crystal field stabilization energy, right? It's crystal field. So usually people also call it crystal field splitting energy because there's a splitting which is happening, but it's also determines the stability of the complex. So that's also called crystal field stabilization energy. In this case, another thing which we should also remember. Just a moment. Yeah, should I erase this part? So another thing which we should remember in this case is that the pairing or unpairing of electrons in this case, for example, I have D4 configuration, which means that I have 4 electrons in D. If they are in ground state, all the 4 will have same energy and all the 4 will have very low energy. If they are in spherically symmetric state, all the 4 electrons will have same energy, but all the 4 have high energy. But if they are present in octahedral field, in such a case they have not 5 orbitals which have same energy, but they have 3 orbitals which have same energy and other 2 orbitals of the same energy. So if I start filling the these orbitals as per electronic configuration rules, so as per Aufbau rule, I'll fill the lower energy orbitals, which means that I'll fill this one and this one, right? Which rule I've used here? One is Aufbau, another is Und's rule, which says that the pairing of electron will not start until you fill all the orbitals singly, right? So I've applied the Und's rule here. Now, for the 4th electron, there is a choice. The 4th electron can either pair here, or this 4th electron can choose to take up this orbital, right? So this is something which we have to understand. On what parameter this decision will be made by this electron. So 4th electron, if pair here, it has to spend, or it should have P amount of pairing energy. So this is the amount of energy which is required for the pairing here. Now, instead, if this electron feels that, oh, why not I go to the orbital of higher energy, at least I don't have to pair. But in such a case, because it is going to the higher energy orbital, it should be able to compensate for the energy gap, which means delta O, that is CFSE. Now there are two situations. One is delta O is greater than P and another is delta O is less than P. If energy required to go to the higher energy orbital, then and more than pairing, then electron will prefer that pairing कर लेते हैं, because energy required to go to the higher energy state will be high, right? If the energy required to go to the higher state is lower than the energy required for pairing, it will say why to pair if I can have one orbital completely and I can remain there singly. So it will excite to go to the higher energy orbital. So when your CFSE is low, this is like low CFSE. In such a case, electrons do not pair up, and we can say that spin of the complex remains high. So such complexes are usually high spin complexes. When CFSE is high, in such cases we can say that if CFSEs will be high, then in such case electrons will be bound to pair up, and as I can see now there are only 2 electrons which are unpaired, so total spin of the complex will be low. So these are low spin complexes. Got it? Yeah, please note it down. Done? Should I erase it? One more thing which we should understand here is, let me just redraw this portion, have a cleaner picture here. Right. So now, as I can see, because of the octahedral symmetric field, energy of all 5d orbitals increased, but did not increase equally. The 3 had same energy and the other 2 had same energy, which we can see. But with respect to the spherical symmetric field, the one got stabilized, or one got lower energy, another got higher energy. So can we quantify how much increase and how much decrease has happened? Yes, we can. अगर ये total value delta naught है, so we can divide the two in portions of energy which we have observed in all the cases. So whatever increase in whatever the value of CFSE, it will get divided into 2 cases. One is this will be 2 by 5 of delta O, and this will be 3 by 5 of delta O. Right, or you can say that 3 by 5 means 0.6 times of delta O, and this is 0.4 times of delta O. So this point is usually also called Berry center. So we can say that the energy of these 2 d orbitals have increased by 60% of the total gap, and this has decreased by 40% of the total gap. Now, how this thing helps us? This thing also helps us in calculating the total CFSE for a configuration. ठीक है? तो एक काम करते हैं, let's just calculate the CFSE value for the 2 cases. ठीक है? तो कैसे निकाल सकते हैं? Here, let's suppose I have D4 configuration. I also have D4 configuration in the 2 cases. ठीक है? When the pairing energy will be lower than the CFSE value, in such a case, what will happen? If CFSE is high, then complex will be low spin, which means that pairing will happen. In such a case, you will have 4 electrons arranged in this fashion, right? This can also be written as, for this case, it can be written as T2G3 T2G4 EG0, right? So in such a case, if I want to calculate the total CFSE for such a case, for this situation, then it will be equal to 4 electrons present in minus 0.4 delta O and 0 electrons present in 0.6 delta O. So for none of the electron energy increased actually, but for 4 electrons energy decreased and has gone to this state, so it will be minus 1.6 delta O. This will be your CFSE, right? Now, but if I calculate it for the D4, it is the case where the pairing did not happen and one of the electron has gone to EG. In such a case, the D4 can also be written as T2G3 and EG1. So for 3 electrons, energy has decreased, which is minus 0.4 delta O, and but for 1 electron, the energy has increased 0.6 delta O. So it will be how much? Minus 0.6 delta O. Right? So as I can see, the decrease in total energy is higher in this case and lower in this case. So by magnitudinally, the CFSE is higher. Right? Similarly, you can calculate in the other cases of tetrahedral or square planar complexes. Right? So this is what we have understood about the octahedral complex. Now let's quickly move to the tetrahedral complex and the square planar complex. Should I erase the diagram portion? CFT in tetrahedral complexes. Right? So if we have tetrahedral complexes, let's see how CFT will work in this situation. So in such a situation, let's first understand how a tetrahedral complex will be applying its field. You can imagine just a cube. Right? And then just imagine there are 3 axes passing through it. This is y axis, this is x axis, and this is z axis. Right? All of them are merging at one point, which is in the center. Right? Now, if I have to see the position of ligands which are coming to form a coordinate bond with the metal ion present at the center. So let's suppose where a metal ion is present at the center of this cube. Just say we study in solid state, so body center is the position, for example. So metal ion is present at the body center and 4 ligands are coming to form bond with it. So from which direction these ligands will be coming? No, they'll not be coming on the axis, because if they'll come on the axis, the angle between them will be 90 degree. But in tetrahedral complex, the angle is 109 degree, 28 minutes. So which can be achieved if the ligands are coming from alternate corners. For example, this corner, not this one, then the alternate one. So this is the adjacent corner, this is the alternate corner. So 2 are coming from this corner and the other 2 are coming from these corners. So if they'll come from these directions, so as I can see, none of them are coming from the sides of axis. You can also see it through a different way. Let's suppose if this is the, for example, tetrahedral geometry which we understand, right? It's like a tripod stand in there. Now what I'm saying is that let's just see this picture like this, right? Now my metal ion is present where these 4 bonds are joining, and these tips or pen caps are denoting the position of ligands from which it's coming, right? Now just imagine the 3 axes which are passing through my hand. So one is the y-axis which is going vertical, the one is the x-axis which is going horizontal in this direction, another is z-axis pointing towards you, right? So as I can see, this ligand is neither coming from the direction of y-axis nor from the x-axis, but somewhere in between. This one is also not coming from the y or x, but somewhere in between. This is also not coming in the direction of y or z, but somewhere in between z and y. This is also coming from somewhere in between z and y. So as I can see, so these ligands are not approaching the metal ions from the direction of axis, but somewhere in between these axes. And as we know from the 5d orbitals, dxy, dyz, dxz, for example, this is x-axis, y-axis, y-axis, z-axis, x-axis, z-axis, right? So these are the orbitals which are actually present in between the axes. So if our ligands are coming from the direction somewhere in between the axes, not on the axis, they will be impacting these orbitals most, and the orbital which are present on the axis, for example dx2 y2, this is present primarily on x and y axis, but my ligand is coming somewhere in between the axis, so it will be impacting these orbitals lesser in comparison to these three orbitals. Same will happen in the case of dz2, where its 2/3 of its density is present on the z axis and the rest on the x and y axis in the form of a ring. So if ligand is coming from the direction which is not on the axis, so it will be impacting these two orbitals less and these three orbitals more, which means now there will be more increase in energy of these three orbitals and less increase in the energy of these two orbitals. So if I draw the energy diagram, can I erase it? So if we draw the energy diagram, so we can say that the energy of 5d orbital is same in ground state. This is ground state. Energy of all the 5d orbitals will increase, but increase equally. This is in spherically symmetric state, right? And if the field is not spherically symmetric but tetrahedral, then in such a case the splitting of energy of these 5d orbitals will happen, but will happen in a different fashion this time, and that will be the energy of the 3d orbitals, which is dxy, dyz and dxz, will increase with respect to the barycenter, and the energy of the other two d orbitals, which is dx2 y2 and dz2, will decrease with respect to the barycenter. So as we saw in octahedral field complexes, this was called T2G and this was called EG. So here we do not use the term G, so this is simply T2 and E. Right, so this set is called T2, this set is called E, stands for the doubly degenerate and triply degenerate orbitals. And the energy gap between the two is called delta T. Again, delta T refers to crystal field stabilization energy for tetrahedral complexes. Or you can say with respect to tetrahedral field. So this is the energy diagram for d orbitals in presence of tetrahedral field. Right? Now, if we want to relate the energy gap with respect to the barycenter, so this is 2/5 of delta t, and this is 3/5 of delta t. Right? So if I want to calculate the total CFSE, and if I have electronic configuration, so I can arrange that. So let's suppose I have, for example, D4 electronic configuration. So I have 4 electrons which I have to arrange in these 5 orbitals in tetrahedral complex. So what I'll do is I'll start filling the electrons from the lower energy orbitals, which is E. So one will go here, another will go here. I'm following Aufbau rule and Unz rule. Then the third electron will have a choice of either pairing up here. I'm just removing this so that it should not create a confusion. Yeah. So the fourth electron will have a choice either to pair up here or to go up here. Right? So this choice can be figured out using the same case where whether delta t is more than p or delta t is less than p. If the energy gap is higher than the pairing energy, then in such a case pairing will happen. If energy gap is lower than that of the pairing energy, then electron will excite and go up there. So in such a case, for D4, E2, T2, 2 will happen. This is the case when no pairing will happen, which means high spin. This is the case which I've drawn there. Can you relate to it? Great. So I'm changing for the another case. Now another case is that the energy gap is higher than the pairing energy. If such a case is there, then electrons will prefer to pair up than going up. So in this situation, it will be E4, T2, 0. And as I can see, there is 0 spin. So in general, such cases show low spin complex. So same stuff which we have done in octahedral complex. So I'm doing the same thing here, right? So did you get it? Clear? Just quickly note it down, then when we'll move to the square planar complex. Done? So let it be here. So because we'll be using it just again, 2, 3, 4, 5. So another is square planar complexes. Right? So what happens in square planar complexes? A metal ion binds with 4 ligands which come from the direction of x and y axis. So let me just redraw so that you can understand it pretty well. So one ligand is coming from the direction of x axis, for example, positive x axis direction. Another is coming from the direction of negative x axis. One is coming from the, for example, y axis. And this coming from the direction of negative y-axis. So 4 ligands are coming and forming a bond with this metal ion. If I join these 4 ligands, it will form a square planar geometry, right? So that's why the complex is called square planar. If I look at the hybridization, it is dsp2. In dsp2, the orbitals which are used is n-1 d x2 y2 s, which belongs to the valence shell. N-1, it means that the d orbital which is used here belongs to the penultimate shell, the second last shell, you can say. And another one is npx and npy. So as I can see, the orbitals which hybridized to form new hybrid orbitals were primarily arranged around x and y axis. Px is completely on the x axis and nowhere else. Py is completely on the y axis, nowhere else. dx2 y2 is completely on the x and y axis, which means they will gel homogeneously and will form hybridized orbital which will be aligned on the x as well as y axis. That is why these ligands are coming from the direction of x and y axis, right? Now if these ligands are coming from the direction of x and y axis, so just forget about the hybridization right now for a moment, because in crystal field theory we're not looking at the hybridization. I was just relating it so that you can understand the correlation between valence bond theory and crystal field theory. So if 4 ligands are coming to bind with this metal ion from the direction of x and y axis, all the d orbitals which have their lobes or orbitals in the direction of x and y axis will be affected more in comparison to the other d orbital which have less electron density in the direction of x and y axis. For example, if I just compare, let's suppose dx2y2. So if these 4 d orbitals are coming from the direction of, let's suppose this axis is x axis, this is y axis. So the d orbital which is on the x and y axis completely, dx2y2, will be affected most. So its energy will be maximum, right? There is another d orbital which is also on the x and y axis, which is on the x and y plane, but not on the x and y axis. It is at an angle of 45 degree to the x and y axis. This is dxy. This will also be affected a lot, but much lesser in comparison to dx2y2. So energy gap will be there, right? So this will be dxy. Now if I look at the dz2, in dz2 the electron density is primarily present on the z-axis. If you remember, I have told you that in dz2, 2/3 of the electron density is present in the lobes of the z-axis and 1/3 is present in the ring, right? So, and that ring is distributed on the whole xy plane. So if the ligands are coming from the direction of xy plane, they'll definitely be impacting this orbital, but not to a very high extent, because electron density on the xy plane is relatively much lesser, A, and that is distributed on the entire plane. So I can say that the energy of, there will be an increase in energy of dz2, but there will be lesser in comparison to. So when I'm saying increase, so that increase is actually with reference to the ground state. I'm comparing it from the ground state. Barycenter will help us in calculating values ki kiska increase kiya, kiska decrease kiya. Although this you can, if that is creating confusion, you can just get rid of this thing and start relating, because this is something which is important, right? Then there are other two cases which we have not used here right now. So that is dyz and dxz. So these two orbitals dyz and dxz have electron density on the plane of yz and xz, and these orbitals are aligned. These orbitals are aligned at an angle of 45 degree to the axis, and ligands are coming on the x and y axis. So in this case, no ligand is coming from the z-axis direction, only one ligand is coming from the y-axis and another from the opposite direction of the y-axis. So only these two ligands will be affecting it. So these two will be affected least. यहाँ पे सिर्फ y वाली डायरेक्शन से जो आ रहा है वो इम्पैक्ट कर रहा है, z से कोई आ ही नहीं रहा है. यहाँ पे जो x से आ रहा है z से कोई आ ही नहीं रहा है. तो इनमें सबसे कम इम्पैक्ट आएगा, which means कि इन केसेस की एनर्जी सबसे कम इंक्रीज होगी, and because of the symmetry and similar impact, the two will have same energy. So dxz and dyz will show the minimum energy here. In the energy gap between these two cases is very small. Right? So this is, so if I look at the energy splitting or the energy gap, this will be the energy gap delta Sp. So Sp stands for square planar. Right? Got it? Is it clear? Right? Now, if I want to compare it with the octahedral geometry, for example, I have a metal ion. Can I just erase this part? Just like creating a lot of mess here. Yeah, now it seems good. So, for example, I have a metal ion to which some ligands can bind, right? And I'm considering two cases. One is that I have 4 ligands forming a square planar geometry, right? Another case is that I have same metal ion, I have same ligands, but they're forming octahedral geometry. Same ligand, same metal ion, right? Because square planar is quite similar to octahedral, or maybe you can say derivative of octahedral. Why? Because for example, if I remove these two ligands, it will be forming a square planar geometry. This is something which we have studied in chemical bonding also. So now the energy gap in this case is delta O, energy gap in this case is delta Sp. So one thing which you should remember about delta Sp is that this value is much higher than delta O for identical cases. In general, for everything to be same, यानी कि सब कुछ सेम है, सारी कंडीशन सब कुछ सेम है, जैसे मेटल आयन सेम ले लिया, सेम लिगेंड ले लिया, बस लिगेंड का नंबर और ज्योमेट्री डिफर कर रहा है, and for example temperature everything else is same, then delta Sp is approximately 1.74 times of delta O. In fact, this gap, the first gap itself is equal to delta O. Right? And so forth, like this is something 0.65, this is something like 0.08. So in totality, it will turn out to be equal to 0.74. Right? ये roughly 0.65 delta O रहता है, 0.66 ले लो, 0.656 रहता है. This is roughly 0.08 delta O, so approximately turn out to be 1.74 delta O. So this gap is very small, this gap is relatively large, and this gap is very large gap. Now, what is the outcome which I can see here? The outcome which I can see here, since the energy gap is high, so the moment you have a situation where the pairing can happen or cannot happen, and like it's like you just like getting confused between whether the pairing will happen or not happen, the energy will be high or low. In such cases, most of the in most of the situations pairing happens. Like for example, let's consider a case of D8 configuration, which usually happens in case of nickel 2 plus. Right? So because nickel has 28 atomic number, argon 18, 4s2, 3d8. So if I remove 2 electrons, they'll go out from the S, and 8 electrons will be left in D. So if I try and if I just keep on arranging these electrons, let's arrange these electrons, 8 electrons here. So it'll come out to be here 1 and 2. Another will go in the higher one because the gap is very small. Then fourth can either pair up here or can go up here. Let's assume they just pair up here. Right? Now the 7th electron will be filled here. Now the 8th electron has a choice of either going here or getting paired up here. As we can see, the energy gap is usually very high, so they often get paired up here, which means this D gets vacant. So this dx2y2 is available. If this dx2y2 is available, if you remember it from the valence bond theory, if this inner d orbital becomes available, so what the other s and p will do, they'll hybridize with it and will form dsp2 hybridization and will show square planar geometry. Or you can say that whenever you have d8, it usually prefers to take the square planar geometry in most of the cases. Or vice versa, that whenever you have dsp2 configuration, the pairing will happen. Or like or in a way, if you have a square planar complex, the electrons will pair up, and then accordingly you'll have low spin complex. Right? Got it? Now let's see what is the application which we can draw out of CFT. Shall I erase it? Factors affecting CFSE. So let's see what are the factors which are affecting the CFSE value. The prime factor which is affecting the CFSE value is the charge or oxidation state of the metal ion. Right? How does it affect? For example, you're forming a octahedral complex. Right? In such a case, you have two situations. One is that you have M2 plus as a metal ion, and in another situation you have M3 plus as the metal ion. If everything else is same, I'm just changing and in fact metal itself is same, but what I'm changing is the charge on that metal ion. For example, in one case I have ferrous ion and in another case I have ferric ion. So as I can see, if the charge on this metal ion is high, then in such a case the charge density on the metal ion will be high and its electric field will be stronger. I'm just using some part of electrostatics here. So electrostatics में आपने पढ़ा होगा that electric field is strong if the charge density on a point is high. So if it has high charge and the size is almost same, or maybe in fact it will be smaller, then in such a case, because of having strong electric field around it, it will interact strongly with these ligands. If the interaction between ligand and metal ion will be strong, then the energy gap will be higher. So higher the charge or higher the oxidation state of metal ion, higher will be the CFSE. So for example, if I'm comparing two geometries, let's suppose one is FeCN 6 3 minus. In this case, 6 cyano ligands are there and they're forming octahedral complex. Another is FeCN 6 4 minus. In this case, 6 cyano ligands are there and they're forming again octahedral complex. Here you have ferric ion, here you have ferrous ion. So if I'm comparing delta O of this complex with delta O of this complex, then this will be larger. Right? So energy gap here in this octahedral complex will be higher because it is Fe3 plus and this is Fe2 plus, and as you can see, rest everything else is same. Both are forming octahedral complex, both are using cyano as a ligand, both are using iron as a metal ion, but only difference is the charge or oxidation state on the metal ion. Can you just erase this part? Yeah. Next is charge on metal ion. So, nature of metal ion. What is nature of metal ion? How does it affect? If I, for example, look at the metal, nickel and platinum, they belong to the same group. So, which means that they have similar properties. That's why they are placed in one group in periodic table, right? Both of them show D8 configuration, and both of them show like D2 plus ion, and they show D8 configuration. In such a case, if you remember that from the periodic properties chapter, when we go down the group in periodic table, for example, I have alkali metals. Let's suppose, or maybe let's suppose I have some boron family: boron, aluminium, gallium, indium, thallium. So when we go down the group, effective nuclear charge. No, in general, by general rule, it remain same ठीक है, it remain almost same. We say which is like there is like almost no change when we go down the group, but in actuality it increases, and especially at 2 points where one is this point यहाँ से यहाँ and another is this point. Why? Because of poor shielding of d orbitals and poor shielding of f orbitals, right? Where exactly this poor shielding of d and f orbitals started? When electrons started going in the d and f orbitals. They started going in d and f orbitals in d block and f block elements. So which means that if I observe the d and f block elements, I'll observe that on going down the group, electrons are going into the d and f orbitals, which means that in a group in d block elements, the effective nuclear charge increases drastically. So there's a sharp increase or drastic increase in effective nuclear charge, which means that, and there is not much increase in size, which means that with the same size, same charge, the attracting power or the field of this ion will be higher than that of this ion. What I'm saying is that, let's just imagine, I have two metal ion M2 plus and for example M dash 2 plus. Okay. M and M dash both are two metal ion having same size, same charge, which means same charge density. एकदम हाइपोथेटिकल केस ले लेते हैं कि दोनों का चार्ज डेंसिटी एग्जैक्टली सेम है. मेरा पॉइंट ये कि इफ द चार्ज डेंसिटी ऑफ द टू इज एग्जैक्टली सेम एंड बोथ आर कंबाइनिंग विद सेम लिगेंड, सेम नंबर ऑफ लिगेंड्स, देन the CFSE value for the two case should be exactly same. But it will not be, because even if the charge density is same, then there is one factor which comes into the play, that is effective nuclear charge. If effective nuclear charge of M2 plus is higher than that of effective nuclear charge of M dash 2 plus, then in such a case delta O for this one will be higher than that of delta O, right? Now how can I relate this thing to the D block elements or F block elements? So as we know, a lot of D block elements form the complexes. So if we go down the group and I am observing, for example, complex of lower group member in comparison to the higher group member, for example nickel and platinum. So if I am observing the complex of nickel and platinum, let's assume everything else is same. For example, I am observing a complex, for example NiH2O whole 6 2 plus, right? And I am observing a complex PtH2O whole 6 2 plus. So we have octahedral complex here, we have octahedral complex here, same ligand, same number of ligands, only difference is the nickel and platinum. So as platinum has higher effective nuclear charge, so its delta O will be higher than that of nickel 1, right? Got it? So delta O increases as we opt for lower member of the group in D block elements for identical conditions. ठीक है, अगर सब कुछ सेम लेते हैं, सिर्फ मेटल को बदलते हैं, और मेटल हमने कैसे बदला है, हायर मेंबर से लोअर मेंबर की तरफ जा रहे हैं, यानी कि ऊपर से नीचे की तरफ जा रहे हैं ग्रुप में. And in such a case I have used the metal which has high effective nuclear charge, so that metal with the high effective nuclear charge or the lower group member will be showing higher energy gap of CFSE. Right? Now let's move on to the other case. Should I erase it? Third is number of ligands. What is number of ligands? For example, a same metal ion is forming an octahedral complex, and the same metal and ligand combination is forming tetrahedral complex, right? The metal ion is same, charge is same, exact same metal, same ion, same charge, same ligands, only difference that here you have 6 ligands and they are forming octahedral complex, and here you have 4 ligands and they are forming tetrahedral complex. Now As this same metal ion is surrounded by 6 ligands, so interaction will be stronger and the energy gap will be higher. And the same metal ion is surrounded by same 4 ligands. Since there are lesser number of ligands, so interaction will be relatively weaker, energy gap will be weaker. So remember this thing as another important fact, that delta O is much more than that of delta T for identical situations. In fact, if I just want to quantify it, so delta T is 4 by 9 times of delta O, approximately 0.44 times of delta O. Right? With this you can also remember one more fact, which is, as you can see, delta T is quite lesser than that of delta O, which means that CFAC or energy gap in tetrahedral fields are very small in comparison to, it is lesser than the half of energy gap in octahedral field. If the energy gap is lower, then there would be high possibility of not pairing up because their energy gap is low. So instead of pairing, they would prefer to go up. So that's why you see less cases of pairing in tetrahedral complexes, but more cases of pairing in octahedral and square planar complexes. Right? So I mean, if you can see, for example, I discussed this example MnCl4 2-. So in such a case, tetrahedral complex is formed, and in such a case, you can also explain it through the CFT. Right? So this is another reason. So this third factor. Fourth factor is, not sure, erase it. The fourth factor, which is the most important factor, that is the nature of ligand. What kind of ligand you are using? So on the spectrochemical data which we have arranged the ligands on their basis of their field, weak to strong. That's a lot of ligands. I'm not writing all of them. I'm just writing a gist of it. You can just refer it from the NCERT that what is the order, and you should remember most of it. But in general, to remember it, the halide donors, like for example F minus, Cl minus, Br minus, I minus. So the halide donors are weaker ligand than which one? Oxygen donors. And which are weakened ligand than nitrogen donors, and which are weakened ligand than carbon donors. Now, the halide donor, oxygen donors, nitrogen donors, or carbon donor does not mean that they're donating halide or nitrogen or oxygen. It means that I'm referring to the atom which will be donating its electron pair. For example, here it will be fluorine, chlorine, bromine, or iodine. So I'm referring to these ligands. Fluoro, chloro, bromo, and iodo. Oxygen donors means I'm referring to donors like hydroxyl in which oxygen atom will be donating. H2O, for example, oxalato C2O4 2-, in which oxygen atom will be donating the electron pair. Nitrogen means, so I'm talking about, for example, amine, in which nitrogen will be donating the electron pair, for example, NO2, right? NC minus, isocyanato, right? Now, the carbon donors refers to the ligands in which carbon atom will be donating the electron pair, for example, Cn minus and CO. So this is a generic trend which you can observe, but yes, it's not the case that it can be remembered. Like for example, if you can see, H2O is a stronger field complex than OH minus, though it seems like it has a negative charge, it should have higher. So that phenomenon does not hold true uniformly. It changes, so it's better to remember the whole trend, right? So on the basis of 4 parameters, I can predict that which complex will have higher energy gap and which complex will have lower energy gap. Now the question is how it helps us knowing that which complex has higher energy gap and which has lower energy gap. Point 1, I can predict whether the complex will be high spin or low spin. Like for example, if you remember, in valence bond theory, we did not say that NH3 is a strong ligand or strong field ligand, right? Sometimes NH3 was showing pairing, sometimes NH3 wasn't showing pairing, which means that if I have to explain why it is showing pairing in certain complexes and not of showing pairing in other complexes. So that can be explained easily using CFT, right? So, for example, in case of CONH3 whole 6 3 plus, it shows pairing. The reason is NH3 is a moderately strong ligand, and you have cobalt ion with a 3 plus charge, which is a quite a high charge, right? 3 plus and 4 plus, they are very, which means it's a very high charge or high oxidation state on the metal ion, and the interaction will be quite strong, and then again the energy gap delta will go very high and will result in pairing of electrons, which will not happen, for example, with some other metal, in which the energy gap will not be very high, right? Point one. Point two, the another achievement of, you can say, CFT was to explain the color of these coordination compounds, right? Why one compound is showing one kind of color and another is not showing another kind of color. Can you just erase it? So next topic is color in coordination compounds. So now let's understand what is happening. So as we know, the 5d orbitals have got divided into two energy levels. So there are two degenerate energy levels. One is called T2G, if I'm referring to the octahedral case, delta O, right? And let's imagine that I have an electron here in the T2G level, and the rest, all the orbitals are empty. Okay? If this complex, so this is the energy level diagram of d orbitals in an octahedral complex. Right? Now, if for example visible light falls on this octahedral complex, then what will happen? This electron may absorb one of the photon which is sufficient for it to excite and go to the higher energy state, right? This is true. And all those other radiations whose photon have higher or lower energy, which were not sufficient or were not eligible to excite this electron, will come out as it is, right? So what happened is that I actually sent, let's suppose, 10 radiations, but what came out was 8 or 9, combination of 8 or 9 radiations. Just take an example. Obviously they're not 10, they're not 8 and 9. These are like thousands of radiations, and these are again thousands of radiations, but showing a color band of 7 colors with Gyore, which we represent in the visible spectrum. Now let's assume that this energy gap was equivalent or closer to energy provided by photons of yellow color, right? So let's suppose, so there is a radiation. For example, I have a yellow color radiation. I'm showing it in red, right? So there's a yellow color radiation which is there. This will get absorbed by this electron and it will not come out. I mean, if it wouldn't have got absorbed, it would have come out here, but it had got absorbed, so it will not come out, right? Is this clear? Now, point one. Point two, the mixture which is coming out is not a complete visible light. It's a mixture of radiations which has different color radiations, but it is not visible light, because some color radiation is missing. It will now show me a specific color. Now you may wonder that, I mean, though it has mixture of radiation, so it will not show you one specific color, but show you a mixture of colors. But it does show me a specific color because of the, I mean, the way our eye work, our eye see the colors. So from the mixture of radiation, our eye, for example, would perceive violet color, right? And will actually reject all the other colors, like red, blue, green, all the others which are coming. It will just simply reject them and will say that the radiations which are coming are actually of primarily violet color. So what color will be observed by our eye will depend upon the combination here, right? Indirectly it also depends, because this combination was created by the radiation which got absorbed. क्योंकि for example ये पूरा का पूरा आ रहा है, इसमें से कुछ गायब हो गया, बचा जो सेट है वो बचा हुआ सेट डिपेंड कर रहा है किस पे, जो एब्जॉर्ब हो गया. So in a way यहाँ the color which you are observing here depends upon the color which got absorbed here, right? So one is color observed, the color which you are observing. Another is color absorbed, the color which is getting absorbed. So they work in a complementary fashion, which means as I have used the example here, the violet and yellow actually work in tandem. So if yellow get absorbed, the complex will appear to be violet. Either the complex is a solid substance or its solution will be violet or purple in color. And similarly, if the violet radiation would have got absorbed, the complex would have been would be yellow in color, or its solution will be yellow in color, right? So how can I predict the color of the complex? Let's see. And what kind of questions can be designed on this concept? Should I erase it? So एक कलर व्हील हम लोग ड्रॉ करते हैं, ठीक है? सो कलर व्हील है, लेट्स सपोज जस्ट एक सर्कल है मेरे पास, और इस सर्कल में 6 क्वाड्रेंट्स मान लीजिए, ठीक है? ये बहुत सिंपलिस्टिक फॉर्म ऑफ कलर व्हील है. द कॉम्प्लेक्स फॉर्म हैज मोर क्वाड्रेंट्स, राइट? And now let's just imagine it as simply a circle which is divided into 6 segments and 6 equal sectors. Now you remember Vibgyor, right? Just ignore the indigo. Let's assume that it has got merged with violet. Just to remember. It's just a jugaad to remember it, right? So violet, blue, green, yellow, orange, red. Just in one fashion, you just try and allot these colors to each quadrant. Now what is the advantage of this? So this is blue, this is orange, this is yellow, green, this is red, and this is violet, right? Now the advantage of this color wheel is that you just have to look for the quadrants which are, or the sectors which are opposite to each other, like blue and orange, red and green, and yellow and violet. So if yellow will be absorbed, the complex will appear to be violet. If violet is absorbed, the complex will appear to be yellow. If red is absorbed, then complex will appear to be green, and vice versa. If orange is absorbed, then complex will appear to be blue, right? Now ये तो हो गया exact एकदम sharp colors. Now let's imagine the shades. For example, the complex is absorbing some set of radiations which are in between orange and yellow. So its color will be somewhere in between violet and blue, right? If it's absorbing the greenish, green and yellow radiations, so its appearance will be red and violet, and vice versa. That yellowish green is the color of the complex, or for example bluish green, or reddish orange, right? So we the kind of shade which we use. Got it? So this is one aspect of color, but another interesting aspect which will relate with the CFT is yet to be discussed. वो अब डिस्कस करते हैं. Done? Now, see, if I look at the Vibgyor, these refer to the color bands of radiations present in the visible light. And if I look at their order, so on going from violet radiations to red radiations, wavelength increases or frequency decreases or energy decreases, which means that the violet radiations have higher energy than that of indigo and that of blue and that of green, yellow, orange and red, right? So the energy of these radiations decreases from violet to red. If this is the case, then if for example I have two situations, in one situation red is getting absorbed, I mean for example the red radiation is getting absorbed, which means that the energy gap already present is a low energy gap and low energy radiation photon is getting absorbed. ठीक है, कलर क्या ऑब्जर्व हो रहा है अभी भूल जाओ, अभी हम बात कर रहे हैं सिर्फ एक सेगमेंट पे कि that if visible light will be passed through such complexes, then in the process of transition of electron from one D degenerate set to another D degenerate set will be of what color. So वो color decide होगा इस energy gap से. If the energy gap is low, then low energy radiation will be absorbed. ABSORBD, absorbed, right? If energy gap is high, then a high energy radiation will be absorbed. Is this true? Is this clear? Right? Now, so what color will be observed can be predicted by the color wheel graph, but the most important thing which you have to focus upon is that what color will be getting absorbed, because here your knowledge of CFT lies, because you can then predict whether the energy gap will be high or low, right? So for example, if the energy gap is high, it will be absorbing violet color and the complex will appear yellow. If the energy gap is low, it will be absorbing, for example, yellow color and complex will appear to be violet, right? Now let's see what kind of questions can be designed. So we have just discussed two cases, two things after CFT. So in CFT I've discussed one thing, which is that factors affecting CFSE values, and another is color of the complexes. Now I can relate the two. Let's see how I'm relating the two. Can I just erase it, this portion? I have two complexes, VH2O whole 6 3 plus and VH2O whole 6 2 plus, right? One of the complex is yellow in color and another complex is in violet in color. You have to tell me, for example, name of this complex, let's suppose is A and this is B. So which will show which color? Hmm. The which one? A? A will be violet in color. A will be yellow in color, and B will be violet in color. This is the right answer. So how we can predict? Let's see. So as I can see, both of them are octahedral complexes. Both are using same ligands, same number of ligands. Both are using same metal ion. The only difference is the charge on metal ion. So as the charge on metal ion is higher in this case, so delta O will be higher in this case. If the energy gap is high in this case, so high energy radiation will be absorbed. Now as I can see, only two colors are being observed here. One is yellow, another is violet. So the one which will be observed as yellow, or one which will appear as yellow, would have absorbed violet in color. So color absorbed आपका कौन सा है इसमें? Violet. और इसमें color absorbed कौन सा है? Yellow. So you have to see it from this way, that since the high energy radiation will be absorbed in the cases where the energy gap is higher, and low energy radiation will be absorbed in the cases where energy gap is low. So yellow will be absorbed here, and the compound will, or the complex ion will appear to be violet in color. Here violet will be absorbed and it will appear to be yellow. Right? Similarly, for example, I can create examples like, let's suppose NiNH3 whole 6 2 plus NiNH3 whole 5 Cl plus. Right, let's suppose both of them form again a yellow color solution and violet color solution. Right, so which one will form yellow color solution and which one will form violet color solution? This will show yellow color solution. So again, as I can see, both have octahedral geometry. The metal ion is same. Here it is nickel 2 plus. Here also it is nickel 2 plus. The only difference is in the nature of ligand. Here all the 6 ligands are amine. Here 5 ligands are amine and 1 is chloro. And as we know, chloro are relatively weaker ligands in comparison to amine. So I have replaced one strong ligand by a one weak ligand. So here the ligands are stronger, the energy gap will be higher, and here energy gap will be lower. If energy gap is higher, it will be absorbing high energy radiation, which will be violet, and thereby it will appear to be yellow. Herein energy gap is lower, it will be absorbing yellow, and thereby will appear to be violet in color. Now one thing which you should remember is that though I am again and again taking an example of yellow and violet, it does not mean that always whenever the gap is higher, it will be absorbing violet. Why I could narrow down on yellow and violet? On the basis of the color choices given to me. So this will be given to you in the options, because otherwise you cannot predict which color will be absorbed. For that you need to know what is the energy band or energy gap precisely by number, and you should also know, for example, what is the wavelength of radiation which is available, which is getting absorbed. Achha, so similarly, as I have just quoted, a question can be designed on this way also. I mean, I can tell you that this is the amount of energy gap there, and calculate the wavelength of the radiation or wavelength of the photon which will get absorbed. Very simple question. I mean, hc by lambda will be equal to that delta, or you can calculate lambda, and then such question can be designed. Yes, the color choices for just choosing the which one will show which color, what you should do is, you should see what kind of color choices it is asking for, and these are the colors which is color observed or color appeared to be. Just look for the color which is getting absorbed, that will be the complementary color, and on the basis of that you just predict the energy gap. Now try and relate the energy gap, which is the CFSE values, from the factors which we have studied. तो उनमें से किसी factor पे comparison हो रहा होगा. जैसे यहाँ पर what I have done is on the basis of metal ion. So similarly जैसे मैं nickel platinum पे play कर सकता हूँ, keeping everything else same. Another factor was ligands. Another factor, for example, was number of ligands. So octahedral and tetrahedral complex. right? So on the 4 cases, I can just play around and form questions, right? Should I So next topic is isomerism in coordination compounds. Right? Isomerism as a concept has not changed from organic to inorganic, it has remained same. So if you understand the concept of isomerism in organic pretty well, you can understand it very easily. So isomerism is, what is isomerism? Structure will be same molecular formula but different structure formula. Will this be the case always? हमेशा ऐसा होएगा? फिर? So isomerism is a phenomena in which the compounds have same molecular formula but different properties. Very true. But different properties. These properties can be optical, these properties can be, or in general, physical or chemical. So it may be entirely different compound on the basis of the drastic difference in their chemical properties, or it may be some very similar compounds but small difference in their physical properties. Like for example, optical properties. One rotates the plane of light in the right direction, another rotates in the left direction. So, but they have same molecular formula but different properties. Can you list the order of consideration of factors if many are present in the compound? Okay, so there is a small doubt related to the CFT which we were discussing. That is that if we can list the order of consideration of the factors if many factors present in the compound. Not really. Usually that whenever we are comparing the energy gaps, we usually do it on the basis of one single parameter. Either that will be the charge on metal ion, or it will be the type of metal ion, or it will be on the nature of ligand, or it will be on the, for example, number of ligands. But yes, if I try and form a combination of 2 or more than 2 factors, then how can I arrange? How can I see? So there would be 2 situations. One situation is that all these factors, for example, I'm using, let's suppose, all the 4 factors, or maybe I'm using, for example, 2 factors. For example, let's suppose I'm using, in one case, ligand is same, number of ligand is same, right? So the 2 factors are removed. The only factor I'm taking is, I'm taking 2 factors. One is, I'm taking 2 different metal ions belonging to same group. So definitely the platinum will show. And in case of here, in nickel I'm using Ni2 plus, but in case of platinum I'm using 4 plus. In such a situation, what I'm doing is that I'm comparing 2 factors, but both of them are actually favoring platinum 4 plus. On the basis of charge, this will show higher energy gap. On the basis of higher effective nuclear charge, this will show higher energy gap. So this will definitely be the easier case of comparison. So whenever you're using 2 or more than 2 factors, you can definitely use, or a question can also be asked, till the time these factors are favoring each other. Which means that if I'm, for example, applying 3 factors, all of them are referring to one particular case, then definitely you can compare. But if these 2 factors would have been aligned in a reverse manner, then it becomes very difficult to compare subjectively, right? Because it will completely depend upon the then data which we are getting. For example, I'm using Ni4 plus and platinum 2 plus. Now in this case, since the charge value is very high, I can say that the factor of effective nuclear charge subjectively should not be dominant over the charge factor, because this is double the charge. So possibly this should be the case. This may not be the outcome. I mean, in this case, this seems like this would be the true, and most likely this will be true. But in certain cases where, for example, the charge difference is not very high. For example, I have one metal M1, I have metal 2. This is 3 plus, this is 2 plus. On the basis of effective nuclear charge, M2 would have win. On the basis of the charge, M3 plus would win. So we cannot compare, I mean, which would win. So that would vary, right? Similarly, on the nature of ligand and so on. So it becomes slightly difficult to compare when you have more than one factor but all of them are opposing each other. If you have more than one factor but all of them are favoring to one case, definitely you can compare. So you can see that this complex A will have higher CFSC value than complex B because of 1, 2, 3 reasons. All of them are pointing towards the same conclusion, right? So let's now quickly come back to the isomerism in coordination compounds. So as I said, isomerism is a phenomena in which molecular formula is same but properties are different, right? So if properties are different, then these properties can be different on the two bases. One is difference in structures, and that results to structural isomerism. The another difference in property could be because of the difference in spatial arrangement, and that results to stereoisomerism. Right? Now what is structural isomerism? The isomerism, or the same concept, like same molecular formula but different properties, that is arising due to difference in structure. And stereoisomerism is the isomerism due to difference in spatial arrangement. That is arrangement of particles in three-dimensional space, which means that when I'm talking about stereoisomerism and I'm comparing the compounds, they have same structure, but there's the arrangement of particles in three-dimensional space is different, and that is the reason why they are showing the isomerism, right? Just before going ahead, because whatever I'm talking about, this is also valid in case of organic chemistry. So whenever you talk about the structural isomerism, since the structure is different and in this case shape or the spatial arrangement will be different, we should understand what is the difference between structure and shape of molecule. The structure of molecule relates to how one atom is bonded to another. It does not relate to the shape or three-dimensional orientation of the molecule. For example, let's see, I mean, from the organic, let's suppose I have C2H6O. This is the molecular formula. Related to this molecular formula, I have two compounds. One is CH3OCH3, and I have another compound CH3CH2OH. So as I can see, this is alcohol and this is ether. Now what is the difference? The difference is in between the structure. Here the oxygen atom is bonded to two carbon atoms. No carbon atom is bonded to another carbon atom. Here carbon atoms are bonded to each other. An oxygen atom is bonded to only one carbon atom and also with one hydrogen. Here it is not bonded to hydrogen. That's why it does not have acidic hydrogen, and this has acidic hydrogen. Because of the same reason, it shows hydrogen bonding, it does not show hydrogen bonding. So there's a difference, drastic difference in their properties, because how one atom is bonded to another has changed drastically. So whenever we talk about structure, what we say is that what has changed is how one atom is bonded to another. For example, I mean, in my hand, let's suppose I have different portions of bones. So the structure is referring to how one is connected to another. ऐसा नहीं कि मैंने ये पाम वाली बोन्स को यहाँ लगा दिया और इसको यहाँ पे लगा दिया, right? तो अगर मैं लगा दूंगा तो वो कुछ अजीब ही बन जाएगा. But the structure is defined. But अगर मैं इसको ऐसे रख रहा हूँ तो ये डिफरेंट ओरिएंटेशन है, मैं ऐसे रख रहा हूँ तो डिफरेंट ओरिएंटेशन है. तो स्पेशल अरेंजमेंट क्या है कि वो जो पार्टिकल्स हैं, जो भी एटम्स हैं, जिनसे मिलकर पूरा मॉलिक्यूल फॉर्म हो रहा है, what is the three-dimensional geometry they are following, that is referring to the spatial arrangement. And when I'm talking about the structure, how they are connected, that is important. How they are arranged in space is none of our concern the moment I'm talking about structure. So in structural isomerism, what will change is how one particle is bonded to another. In spatial arrangement, structures will remain same. For example, let's suppose I have CH3CH double bond CH CH3. This is 2-butene. the structure is exactly like same in two cases. Case 1, I have cis 2 butene. Case 2, I have trans 2 butene. So as you can see, CH3 CH CH CH3 CH3 CH CH CH3, exactly same structure. So the two cases have identical structures but not identical spatial arrangements. Spatial arrangement is different. In this case, two larger groups, which are CH3 or same groups, are on the same side of double bond, and here in these two groups which are on the opposite side of double bond, that's why it's called trans and this is called cis. And because of this arrangement, their properties are different. For example, it has zero dipole moment, it has some dipole moment, it is slightly polar in nature, it is completely non-polar in nature. It has symmetrical geometry, it has relatively less symmetrical geometry, and for that reason there lot of such properties vary. Clear? So this is what happens in stereoisomerism. Now let's see what kind of structural isomers or structural isomerism we observe in case of coordination compound. Can you just quickly erase it? Structural isomerism in coordination compounds. So one is, for example, ionization isomerism. What is ionization isomerism? I'll explain it with an example. For example, I have a complex CO NH3 whole 3, or for example NH3 whole 4 ClBr Cl. Right? So this complex has cobalt 3 plus ion and it has 6 ligands. One is chloro, another is bromo, and 4 are amine. Right? If it ionize, it will give me cobalt NH3 whole 4 ClBr plus and Cl minus as ions. Right? There's another complex which seems to be very same, but it's not, because if it will ionize, it will give me Br minus instead of Cl minus. Herein, this bromide ion is satisfying only primary valency. Werner's theory, remember that? Or I can say that this bromide ion is not acting as a ligand here, wherein this bromide ion is acting as a ligand, it's called bromo here. So there's a structural difference. This bromide ion is forming a coordinate bond. This bromide ion is only attracted ionically with the cobalt ion. That's why it's ionizable. That's why this is not ionizable, and that's why there is a difference in structure. Similarly, this chloride ion was earlier ionizable and was not bonded to cobalt ion, but now it is bonded to cobalt ion through coordinate bond and now not ionizable. So such kind of isomers are called ionization isomers, and the phenomena is called ionization isomerism. Right? So as you can see, there is a difference in structure. Second is hydrate isomerism. What is hydrate isomerism? For example, I have a complex COH2O whole 6 Cl3. In this case, I have a complex ion in which 6 ligands are aqua or aquo and 3 chloride ions are there. Now let's take the other case where 5 ligands are H2O or aqua and one H2O is outside as a water of crystallization, right? For example, third case, two H2O are outside as a water of crystallization. Now, though this can also be a part of the ionization isomerism, but it's not called ionization isomerism because what specific thing is happening here in this case is that the position of H2O. Here H2O is acting as a ligand, all 6 of them. Here only 5 of them are acting as ligand, but one is acting as a water crystallization. Here only 4 of them are acting as a ligand and 2 of them are acting as a water of crystallization, right? So because of the different positions of H2O, different roles of H2O, but having same molecular formula, this isomerism belongs to the structural isomerism and specifically called as hydrate isomerism. Okay, got it? Third is linkage isomerism. Linkage isomerism is shown by those ligands which are ambidentate ligands. Right? So what are ambidentate ligands? The ligands which can bind from more than one kind of sites, but only one at a time. Right? So either it will be binding through carbon or it will be binding through nitrogen. Either it will be binding through nitrogen or it will be binding through oxygen. So for example, I have a complex, let's suppose FeNO2 whole 6, for example 3 minus, and I have a complex FeONO6 3 minus. So in both the cases I have Fe3 plus ion. In one case I have N-nitrito, in another case I have O-nitrito, or I have nitrito and isonitrito as the name of the ligand. So because of this difference, the two are linkage isomers. Because everything else is same, only difference which has occurred is the linking atom from the ligand. Here the linking atom from the ligand is nitrogen, here the linking atom from the ligand is oxygen. Fourth is coordination isomerism. So what is coordination isomerism? This is the case when we have a complex compound in which the cation as well as the anion, both of them are complexes. I mean, if you remember, we also talked about the nomenclature of these compounds. In such case, for example, in one case I have amine as a ligand which is bonded to cobalt, and in another case I have cyano as a ligand which is bonded to chromium. Let's just see the other case. For example, I have chromium bonded to amine and cobalt bonded to cyano. So the molecular formula of the two is exactly same, but the two are different because here amine is bonded to cobalt and here amine is bonded to chromium. Here cyano is bonded to chromium and here cyano is bonded to cobalt. So such kind of isomers are called coordination isomers. Okay. So structural isomerism is a very simple case to handle. The slight problem which happens is in the case of stereoisomerism of coordination compounds. Stereoisomerism, as we have studied in the case of the organic also, it is either geometrical or it is optical. right? So conformation is not observed here. So the two cases of stereoisomerism are observed here. One is geometrical and another is optical, right? Let's begin with the geometrical isomerism and then we'll come back to the optical isomerism in detail. So we'll be spending most of our time on these two because these are the ones which are usually asked and are slightly difficult to handle. Not very difficult, but once we understand, it will become very easy to just crack. Just quick, can I erase it? Yeah. So let's just focus on the geometrical isomerism. As you could see, we have studied three kinds of complexes. Tetrahedral complexes. Another is square planar complexes. And third is octahedral complexes. These are the shape of most of the complexes. Though they also acquire other shapes, but these are the most common. And you may say that in our scope of syllabus, these are the three shapes which we have to understand, and the isomerism and properties around them. So, so in tetrahedral complex, the metal ion is bonded to 4 ligands two coming out of the plane and one going inside the plane, right? Now, before we move ahead, let's just quickly understand what is geometrical isomerism. No idea. Geometrical isomerism is the isomerism which is observed when the molecule, when the compounds have same molecular formula, same structure, but different arrangement of particles in space. Now, what is that difference which is arranged, or what is that difference in arrangement which is observed here? Because some kind of difference in arrangement will be observed in geometrical and some kind of difference arrangement will be observed in optical, right? So what really happens in geometrical isomerism is that the relative position of the group changes, right? For example, if I just relates to the case of geometrical isomerism, which we have studied in organic compound, because it will become easier to understand from there. Let me just take the same example of 2-butene. In one case, the 2 CH3 groups were on the same side, and in the other case, the 2 CH3 groups were on the different sides, right? So we say that the same groups are present opposite to each other and the same groups are present adjacent to each other. Because they are adjacent to each other, so that's why it's called cis, and because they are opposite to each other, they are called trans, right? So this is the geometrical isomerism, in which what we understand is that with reference to one particle which is arranged in that geometry, that the similar particle or same particle is arranged in whether adjacent to it or to some different position. So this is how we define the geometrical isomerism or observe the geometrical isomers. Let's see the geometrical isomers in coordination compounds. ठीक है? So मैंने कहा कि सबसे पहले बात करते हैं coordination compounds में tetrahedral complex के बारे में. So in case of tetrahedral complex, what really happens is I have 4 ligands attached to a metal ion, and they are arranged in a tetrahedral fashion. Right? For example, this is how they are arranged. Now, if all these 4 ligands are identical and this metal ion is there in the center, so, and they are forming a perfect tetrahedral geometry, then in this case, the position of this ligand and this ligand, and position of this ligand with this ligand, position of this ligand with the third ligand, and vice versa. I mean, if it's perfect, I mean, if it will rotate, it will be completely identical. So every ligand is equidistant from the other 4 ligands. जैसे अगर मैं इसको ऐसे रखूंगा, तो ये इन तीनों से बराबर उतना ही डिस्टेंस पे जितना ये इन तीनों से है, जितना ये तीनों से है, and so on. So every ligand is equidistant from all the other 4 ligands. So relative position बदल ही नहीं सकती, because if I'm saying that जैसे for example ऐसे समझते हैं, मैथ्स के थ्रू समझ सकते हैं. For example, I have a equilateral triangle. Right? Now, if I place something here and I want to observe कि यार यहाँ पे जो है और यहाँ पर जो है इन दोनों की पोजीशन इससे कितना दूर है, इक्विडिस्टेंट है. अगर even if I change it, doesn't really matter because it will be same. So that is something which is happening here. Since the all positions are equidistant with each other, we can say that even if we replace their positions, there would not be relative change in their positions. They'll not be adjacent or opposite or maybe closer or far, because every time they'll be as close as far as they were initially. So in short, tetrahedral complexes do not show geometrical isomerism. Right? Got it? Square planar and octahedral complexes do show geometrical isomerism, and let's see how do they show geometrical isomerism. Got it? Should I erase it? So let's talk about the geometrical isomerism in square planar complexes. Right? So if you have a metal ion and 4 ligands are bonded to it and forming a square plane, right, then in such a case you can observe the geometrical isomerism if you have a square planar complex in which 2 kinds of ligands are present. For example, ligand A and ligand B. You have 2 monodentate ligand A, monodentate ligand B, and you have this kind of complex. Okay? So A is representing A and B are representing monodentate ligands. Right? So this means that I have 2 ligands which are A and 2 ligands which are B. So in one of the geometry I can see that A are adjacent, but in another geometry the case could be that the ligands A are opposite to each other and ligands B are opposite to each other. So as I can see, here A are adjacent to each other and here A are opposite to each other, or maybe you can tell it in the reference of B. Here B are adjacent to each other and B are opposite to each other. So this will be cis and this will be trans. Got it? Now I can also figure out which cases will not show geometrical isomerism in square planar complexes. If you have 4 ligands monodentate and all of them are same, because if they are same, even if you are replacing their position opposite adjacent, they'll all be same, they'll not show geometrical isomerism. If I replace only one and keep the other 3, then what is the problem which I'll observe? Let's see. In such a complex, since 3 ligands are same and only one ligand is different, so howsoever I change, I'll be forming same geometry. See, if I replace this B with this B, it is the same case, 3A in one line and then 1B in the corner, right? So it is actually the same geometry which you are generating. You'll not be able to generate the other geometry, which means a reverse case of this may be 1 single A and 3 same B. So these 3 cases do not show geometrical isomerism. right? It is very important in understanding science and in general in life that what works, but at the same time what is also important is what doesn't work, right? So this will not show geometrical isomerism. Okay, so what I've understood is that at least so geometrical isomerism in square planar complexes will be observed in at least one simplistic case where you should have two different types of monodentate ligand, and amount which should be present of the two should be 2 2. The moment four of them are same or three of them are same, they'll not show geometrical isomerism. Got it? Now, second thing, let me just take another case where I have two monodentate ligands which are same, and one monodentate ligand which is different, and third monodentate ligand which is also different. So A, B, C, and C are monodentate ligands. So what I've done is I have changed one B by C. So the question is, will this show geometrical isomerism? Yes, it will be, because here the 2A are adjacent to each other and the 2A are opposite to each other. And as I can see, though B and C are different, but the relative position of B and C is adjacent and the relative position of B and C is opposite. So you can see it from the angle. Basically, the adjacent or the opposite positions are actually observed through angles. यहाँ पर इन दोनों के अगर हम पॉइंट ज्वाइन करते हैं सेंटर पे, तो एंगल विल बी 90 डिग्री and here will be 180 degree, right? And so is the case with A. And you can also relate it why we actually omitted the case of tetrahedral, because all the angles will be 109 degree 28 minutes, so the relative positions will be same. So this case will show geometrical isomerism and two geometrical isomers will be observed. Now if I change this A with D, so which means that A, B, C and D, four monodentate ligands are there, all of them are different. Will this show geometrical isomerism? Yes, because all the four of them are different and will be taking different positions. For example, let's take the case of A and D. So here A and D are at adjacent position, here A and D are on opposite positions. B and C are at adjacent position, B and C are opposite positions. I cannot name them to be cis and trans, because to name them to be cis and trans, same group should be on the adjacent position and same group should be on the adjacent opposite positions. But yes, this will show geometrical isomerism. I just cannot name them as cis and trans, but by the logic of geometrical isomerism, they'll be called as geometrical isomers. Not two, but three geometrical isomers will be formed. Right? So you can just remember it. If you want to draw what all four will be there, so one will be definitely M, A, B, C, D. You can just quickly arrange in any fashion A, B, C, D. Then just take it to be B, A, C, D, and then take it to be M, B, C, A, D. So what I've done is I've just replaced the first two, and then I replaced the next two. It will be creating three different arrangements. Okay, none of the arrangement will be same. Right? It does not mean that if I take D, A, B, C, so it will be different. No, it will be same to any of the two here. Because D, A, B, C means, for example, just like A, B, C, D is there. For example, you are saying I'll take sir D, D, A, B, C. It will be different. It will not be different because D, A, B, C means that D, A, B, C, I am moving in this order. D, A, B, C. This is same as that of A, B, C, D. This is same as that of B, C, D, A. This is same as that of C, D, A, B. So all the cases will be covered, right? Whereas if you see, this is different. ये वाला कौन सा है? This is B, A, C, D. Perfect. So if I take it as BACD, DBAC, CDBA, ACDB, all of them will be same, right? So only 3 cases can be made. How can you predict 3 cases? You can remember it simply. What I've done is I've written just them in one order. I've replaced the first 2, and I've created the second isomer. Then in next case I have replaced the other 2, and I have actually created the third isomer. So even if you want to draw it yourself, and though it will never be asked, but if you want to check what 3 distinct cases will be formed, you can remember it this way. So in square planar complex, only these cases will be formed with monodentate ligands. What if I have bidentate ligand? So let me take some notation. So AA represents symmetrical bidentate ligand. Example, C2O4 2 minus. Herein, if you can see C double bond O, O minus, C double bond O, O minus. So this will combine with metal ion from the 2 directions. So this ligand is symmetrical and a bidentate. AB represents unsymmetrical bidentate ligand. For example, glycinato. NH2CH2CO minus. So one ligand, bond or metal ion will be formed from the CO minus, another from the NH2. So this is a unsymmetrical bidentate ligand. Got it? Now let's see what will be the situation which will be observed in the case of geometrical isomerism. If I have symmetrical bidentate ligands, and I have 2 such bidentate ligands, how will I represent them? It's like the 2 are connected. So these curves are representing the bond between AA. For example, C double bond O, C double bond O, O minus, O minus. And this dotted lines representing square planar symmetry. Right? So this case will never show geometrical isomers because all of them are identical. Right? If I have one unsymmetrical bidentate ligand, there's a small doubt in MABCD. As I stated earlier also, in such complexes you cannot use cis trans as nomenclature to name geometrical isomer. This is a very similar case which we understand in organic chemistry also. So when around the carbon-carbon double bond, the 4 groups which you are arranging, if all 4 of them are different, for example fluorine, chlorine, bromine and iodine, so carbon on the carbon-carbon double bond, you cannot use the cis trans isomerism. You use the or cis trans nomenclature to notate the geometrical isomerism. You denote the EZ nomenclature, but we do not use EZ nomenclature in this case, so we do not really name them as ENZ or cis and trans. We just simply say that these are 3 distinct isomers which we are forming. So coming back to the case of the bidentate ligand. So now let's suppose I have one symmetrical and one unsymmetrical, and none of the portion of the unsymmetrical matches with symmetrical one. In such a case, the metal ion will be bonded to a symmetrical bidentate ligand and a unsymmetrical bidentate ligand, and the geometry will be square planar denoted by dotted lines. Right? Now, if I replace this B and C by flipping it, for example, the C is binding from here and B is binding from here, will this change this complex? No. भाई what I'm saying कि अगर मान लो मैं इसको पलट देता हूँ, मैं कहता हूँ कि C यहाँ लगा हुआ है and B यहाँ लगा हुआ है, तो क्या ये कॉम्प्लेक्स बदल जाएगा? No, because this is exactly same as that of the previous case कि बस आपने उस complex को उठाकर ऐसे देख रहे हो. So this is not creating a different geometry. This is exactly the identical geometry, which means that this case and this case do not show geometrical isomerism. Can you erase it? Let's suppose we have two unsymmetrical bidentate ligands. Right now, so there are two cases. One is in that we have unsymmetrical bidentate ligand. Since I'm using the two same bidentate ligands, but though they are unsymmetrical, so because of their unsymmetry, we are creating a different geometry if I place them differently. As I can see, from the unsymmetrical portion, the same atoms, same kind of atoms are on the same side, whereas they are on the opposite side. So they're creating the cis and trans isomers. Can I erase it? Yeah. So you can also create the case which are mixed with bidentate as well as monodentate ligand. For example, will this show geometrical isomerism? Let's treat it as a question. I'll draw it for you. So this is a metal ion. So B and C are monodentate ligands. AA is a bidentate symmetrical ligand. No? Why? So if you change the position of these two ligands, because the problem is that when they were monodentate ligands A, 2, B, C, we could see the geometrical isomerism because you could change the position of 2A. Now, since they being bidentate ligand, they can only join from one side. What I cannot do is that I'll join one A from here and one A from here, and that's fine. It will not happen because the gap between the two atoms will increase so much that it will not be able to form this geometry. And for it to form this geometry as a stable geometry, it will bind from only one side. So which means this is locked. And because it being symmetrical, even if you change it, would not really matter. So you can the only thing which you can change is this. Now this is a case where you're just actually flipping the same molecule. So this will not show geometrical isomer. ठीक है, ये बता दो। Now next is geometrical isomerism in octahedral complexes. ठीक है, so in octahedral complexes we have 6 positions. 4 are forming a square plane, one perpendicularly above the plane, one perpendicularly below the plane. All of them are equidistant from the center. All of them are forming same bond angles 90 degree with each other, and 180 degree with the opposite one. Just like 1 और 6 180 degree बना रहे हैं, 4 और 2 180 degree बना रहे हैं, 2 और 3 5 and 3 are forming 180 degree angle, right? Now in this case, if I observe it from the side of 1, so as I can see, from the position of 1, 2, 3, 4 and 5 all are at equidistant position, right? I mean, if you just imagine, for example, there is a square plane which I am forming here. So 4 groups are here on the square plane, 2 are coming towards you, 1 and 2 are here. 1 is, for example, in the direction of my hand, and this is the perpendicular which is above this plane, square plane. So this position is equidistant from these 4 positions. So I can say that 1 is adjacent or closer to 2, 3, 4 and 5. And for 1, 2, 3, 4 and 5, all of them are equal, because they are at equidistant position, 90 degree angle, 90 degree angle, bond, the length of the bond is same because metal and ligands are same. So all of them are at equidistant position. But for 1, the 6 is far. So I can say that 1, 2, 1, 3, 1, 4, 1, 5 will show cis or adjacent position, whereas 1, 6 will show trans position. ठीक है? So they are far from each other and they are closer to each other. So adjacent and opposite. So adjacent will be 1, 2, 1, 3, 1, 4 and 1, 5. Is this clear? Right? Now, another thing which you should also understand in octahedral geometry, since octahedral geometry being a very perfect and regular geometry, though I have placed 2, 3, 4 and 5 on a square plane and 1 and 6 on the vertical axis positions, right? और apex of the octahedron कि जिनको join करेंगे तो एक ऊपर pyramid बनेगा, एक नीचे pyramid बनेगा, तो 1 and 6 are at the apex of the pyramid and 2, 3, 4, 5 appears to be on the square plane. But इस geometry का perfection ये है that if I flip this geometry, so you would not be able to judge whether you have actually flipped the geometry or not, because every position is identically placed over the other. Like for example, we were talking about this case, like let's suppose this blue marker and the black marker and the other red marker, which you can observe, and my hand, they are in a square plane, and this is the one which is 1. So for example, this is the 1 position, this is 3 in front of you, this is 2, this is 4, 3, 4 and this is 5, and then my hand will be in the 2 position, right? अब मैं क्या कर रहा हूं, मैं इसको flip कर रहा हूं. Now if I flip this thing, then this and this have come up. For example, 3 and 5 have come up. This is 3 and this is 5. Now 1, 2, 6 and 4 will be forming a square plane. Similarly, if I take 4 and 2 on vertical axis, then 1, 5, 3 and 6, they will be forming a square plane. So what all you have to do is you just pick the 2 points which are opposite to each other and just hold these 2 points and do what? कभी ऑक्टेल ज्योमेट्री से लाइक मुझे फॉर एग्जांपल 2 4 को वर्टिकल पे लाना है, तो 2 4 को आपने होल्ड कर लिया एंड 2 4 को वर्टिकल पे लेके आ जाओ घुमा के. What all will happen is 1 5 3 and 6 they'll come on the square plane. In what kind of geometry that you can observe very similar, very simply here, like for example अगर मैं इसे रीड्रॉ करना चाहता हूं कि 2 और 4 को मेरे को यहां लेके आना है. सो मैं 2 और 4 को लेके आया हूं, तो बेसिकली 1 और 5 सामने आ जाएंगे एंड 3 और 6 पीछे चले जाएंगे. राइट. सो 2 4 को मैंने पिक किया, इसको पूरा ऐसे लेके आ गया, 1 5 सामने की तरफ नजर आएंगे और 3 6 पीछे की तरफ नजर आएंगे. राइट. इन सच अ केस आई कैन से दैट 2 3 2 6 2 1 2 5 they will be forming cis, whereas 2 and 4 will be forming trans. Or simply I can say that with respect to any position except the opposite position all will be forming cis. जैसे 2 के रेस्पेक्ट में देख रहा था, तो 2 के रेस्पेक्ट में 4 will be forming trans and rest all positions will be at cis or adjacent. So opposite वाला opposite पे आ जाएगा एंड बाकी सारे adjacent positions पे आएंगे. और ये खाली टॉप से नहीं देखा जाता है, कहीं से भी देख सकते हो क्योंकि सब कुछ सिमेट्रिकल है. ठीक है, गॉट इट. So obviously if I have 6 identical monodentate ligands, it will not show geometrical isomerism. If I have 5 geometrical monodentate ligands as same monodentate ligands and one as different, then again it will not show because the position of B will be symmetric in all the cases. Even if you change the position of B, it will not be able to change with respect to the other case. But MA4B2 will show geometrical isomerism. So these two cases do not show geometrical isomerism. Seriously? So MA4B2 this is the case of MA4B2. This is the case trans where the 2 B atoms are opposite to each other, and in the other case two B atoms are adjacent to each other. So this is cis and this one will be trans. So this is the simplistic form of the or simplistic case of the isomerism in the geometrical isomerism in the octahedral complex, right? So this is MA4B2 type. Right? Now let's look at the case MA3B3 type. When you have two kinds of monodentate ligand and you have 3 of one kind and 3 of another, in such a case two kinds of geometries will be observed. One is for example this one, and another is of this kind, right? For some it may appear that it is also cis and trans because people try and find out cis and trans everywhere, though it's not the case. Uh, this is actually geometrical isomers, but not named as cis and trans, but named as, any idea? Facial and meridional. In short, it's called FAC. In short, it's called MER. So sometimes also called FAC-MER isomerism. Right? Now, what is FAC-MER isomerism? Let's just understand it through the three-dimensional geometry. If you imagine the octahedral geometry, अभी इसको मत लिखो, भूल जाओ, पहले समझ लो. I'll explain you. ये एक बार समझ में आ जाएगा. Just focus here. If you just imagine the octahedral geometry, what you have 4 points which are in one plane, and they are equidistant from each other. So if you'll be forming a square plane. There's one particle which is in the center but not on the plane, and from this point we are joining these 4 points. So I'm forming a square pyramid shape. There's one point which is below, and I'm forming a square pyramid shape on the same square base. So I'm forming a square bipyramidal geometry. एक स्क्वायर बेस है मेरे पास, फॉर एग्जांपल ये ले लेते हैं, तो मेरे पास ये 4 पॉइंट्स हैं, ये स्क्वायर बेस है, एक पॉइंट ऊपर लिया, इससे इन चारों को जोड़ दिया, तो मेरे को क्या मिल जाएगा? स्क्वायर पिरामिड. एक पॉइंट ऐसे नीचे लिया, इससे चारों को जोड़ दिया, तो मुझे क्या मिल जाएगा? स्क्वायर बाइपिरामिड. राइट? If I adjust the height of these 2 points upward and below and position of these 2 points in such a way कि जब पिरामिड बनेंगे तो क्या होगा कि अगर जैसे if you remember the Egyptian pyramid, then बिल्कुल this is the typical case. Egyptian pyramids are square pyramids, right? Square base पे pyramid फॉर्म हुआ है जिसमें जो sides develop होंगी वो triangular faces होंगे. जैसे फॉर एग्जाम्पल इन लाइन्स को भूल जाओ, इनके पॉइंट्स इमेजिन कर लो. If I join this point and this point, so they'll be forming a triangular face. They'll be forming a triangular face. They'll be forming a triangular face. यानी कि 4 triangular faces will be formed in the upward plane, the upper pyramid, and similarly 4 triangular faces will be formed in the below pyramid. Right? If I adjust the height of these 2 pyramids in such a way that all 8 triangular faces are equilateral triangles, then the geometry is called octahedron, and the shapes are called octahedral shapes. Right? So if you have understood octahedral, then you will also understand one more thing about octahedron, that it has 8 faces and all of them are triangular faces. Point 1. Point 2, if I just forget the faces and come to the lines, I mean मैंने अभी थोड़ी देर बोल रहा था कि lines भूल जाओ, सिर्फ points देखो और बाहर की shape को observe करो. Now just forget the outside shape कि वो कैसी बन रही है, triangular बन रहे हैं नहीं बन रहे हैं, just observe the lines. हम ऐसे ये 6 lines drawn कर रहे होते हैं, right? If I see these 6 lines, these are like what? कोई x axis है, एक y axis है, एक z axis है, which means that you will be forming 3 planes. Cartesian system हो गया. Like for example, एक xy plane बन रहा होगा, let's suppose horizontal plane, एक xz plane बन रहा होगा, एक yz plane बन रहा होगा. So there are 3 planes. So in octahedral shape or octahedral geometry, these planes are called meridional planes. Point 1, which will relate to this. Point 2, the faces which we were talking about, the triangular faces, they are the faces of the octahedron. Now, if you observe this B atom, and this B atom, they are present on one triangular face, and the other 3 A atoms are present on the other triangular face. Right? How can you see? Let's see. Let's just observe this in this case. Yeah. Now in this case, so as you can see, for example, one B atom is here, one B atom is here, and one B atom is here. All the 3 of them are joining and forming one triangular face. So they are present on the face of the octahedron. Right? What is about the other 3A? This is the case. The 2A are present at the back and 1A at the bottom. So these are joining and forming one triangular face, which is this one. So all 3A are present on one face, all 3B are present on one face. That's why it's called facial isomer or FAC isomer. Right? Now let's understand the meridional one. What is meridional? The 3 groups should be falling on the same plane or the meridional plane. How can I observe the meridional plane? Anyone which is like, I mean, any 3 cases which are forming on one plane. Like, I mean, if I'm observing this kind of octahedral geometry, 2 are from the at the back, then let's suppose this red and black, the three will be forming, they'll be on the one plane, which is this plane. Let's suppose this is x-axis, this is y-axis, and this is z-axis. So these three positions will be on the yz plane. नहीं समझे? ये vertical को मान लेते हैं z-axis है. This blue one is the x-axis and this red one is the y-axis. So y and z, so this will be yz plane, formed by these two lines or these two axes. So if I have 3 points in octahedral geometry, 1, 2 and 3, they're falling on one single plane, that is yz plane. So since they are on one single plane, which is meridional plane, so such isomer will be called as meridional. Like as I can see, this B and this B, they are in one plane. This A and this A, the three are in one plane, that is horizontal plane. Let's suppose if this is z-axis, this is x-axis and y-axis. So all the three A are present on the xy plane and all the three B are present on the yz plane or one of the meridional planes. So that's why this isomer is called meridional and this is called facial. Got it? So again we have octahedral complex in which we have two symmetrical bidentate ligands and two different monodentate ligands. So in this case, the metal ion, for example, is bonded to two symmetrical bidentate ligands. And they are bonded to two monodentate ligands. Right? So one case could be this, another case could be so as I can see, the two are forming different kind of geometry. Here the two B groups are opposite to each other, and here the two B and C group and B and C groups are adjacent to each other. So these will be two different geometrical isomers. If these B are same, so I can call them as trans and cis. Got it? If I have three symmetrical bidentate ligand, then what will happen? All the cases or positions will be identical, do not show geometrical isomerism. Right, so similarly we can make multiple cases and observe ourselves, and if you find any difficulty in observing the another case, just let me know, we'll explain it again. Now let's move on to the optical isomerism. fish. Okay. There's a doubt around facial and meridional. I'm explaining it again quickly. So now, if you have to understand facial and meridional, you need to understand the octahedron geometry. If you understand octahedron geometry pretty well, so you can easily identify the facial and meridional. So let's suppose you have a point. So you have, for example, 4 points which are forming the octahedral case geometries, and sorry, square plane, and they're like 2 more which are forming the octahedral geometry, right? Let me just redraw it. So let's suppose I have metal ion, 4 ligands are attached to it and attached in a square planar geometry. The one is above the plane, another is below the plane. So it means that I have 6 points in the plane. How these 6 points are arranged in a plane and are forming the octahedral geometry, let's understand that. So I have 4 points, and all these 4 points are arranged in one plane. They're in one horizontal plane, right? If I join all 4 of them, I'll be forming a square base, right? So like I'm forming a square base. Now there is a point above this square base. If I join all the 4 points by the square base, I'm forming a pyramid, just like Egyptian pyramid. That's a perfect square pyramid, right? Practically formed as a large building. So, or maybe Louvre Museum in France. So just like a square pyramid shape, right? If I take one more point at the bottom and form a similar kind of pyramid, I'll be forming a octahedron geometry. So in the octahedron geometry, if you observe the overall geometry, that's like more of a like diamond kind of shape. So in this octahedral geometry, you can see there are 4 triangular faces in the above pyramid and 4 triangular faces in the pyramid below, right? So in totality, you have 8 triangular faces. This is one. Another way of looking at the octahedral geometry is that instead of looking at the faces, if I, for example, am joining all the opposite points inside the octahedron, so what will be observed to me is that this kind of case, where I have 6 points, 4 in one plane, forming a square, and 1 above, 1 below, in which if I join the above and below points, they'll be forming a 2 pyramids, one above plane and another below the plane. So if I just observe the lines which are connecting all 6 vertices, इसमें 6 vertex हैं, 6 को अंदर से join कर दूंगा मैं, तो ऐसा बनेगा. If I observe it, all of these lines are at an angle of 90 degree to each other. सारी lines एक दूसरे से 90 degree पे हैं, right? So if they are at an angle of 90 degree to each other, so this can be related directly to the Cartesian coordinate system. If I relate it to the Cartesian coordinate system, then ये वाली डायरेक्शन में जो एक्सिस जा रही है, फॉर एग्जांपल ये एक्स एक्सिस है, ये वाले में जो जा रही है दैट इज वाई एक्सिस, एंड द अबव द प्लेन इज जेड एक्सिस, एक्स एंड वाई थंब के डायरेक्शन में जेड, ठीक है? सो अगर सो दिस इज लाइक एक्स एक्सिस, दिस इज लाइक वाई एक्सिस, एंड दिस वन इज लाइक जेड एक्सिस, राइट? सो 3 प्लेन्स विल बी फॉर्म्ड, एक्स वाई, वाई जेड, एक्स जेड. अब उसको एक्स वाई की जगह वाई एक्स बोल दो, और वाई जेड को आप जेड एक्स जेड वाई बोल दो, और जेड एक्स को एक्स जेड को जेड एक्स बोल दो, एक ही बात है, कोई फर्क नहीं पड़ता है. सो इन टोटलिटी यू हैव 3 प्लेन्स, एक्स वाई प्लेन, वाई जेड प्लेन एंड एक्स जेड प्लेन. सो इट मीन्स दैट यू हैव 3 मेरीडियोनल प्लेन्स, दे पासिंग थ्रू द मेरिडियन ऑफ द ओवरऑल 3-dimensional ज्योमेट्री, राइट? अब इसको ऑब्जर्व एक और तरीका समझने का, देखो मेरिडियन को समझने का एक और तरीका क्या है. फॉर एग्जाम्पल, इफ आई एम ऑब्जर्विंग दिस ऑक्टाहेड्रल ज्योमेट्री, शेप से भी समझ सकते हो आप मेरिडियनल प्लेन को. The 4 points which are falling on the square plane are actually meridional, are at the meridional plane, and the other 2 points will not be at the meridional plane, right? So these 4 points on the meridional plane. Now, if I, as I explained previously, if I instead of taking these 2 points on the top and bottom, if I take these 2 points on the top and bottom and flip this geometry, other 4 points will come on the meridional plane. अगर मैं कोई दूसरे 2 पॉइंट्स पकड़ लूं और इनको वर्टिकल पे ले जाऊं, तो बाकी 4 हॉरिजॉन्टल पे आ जाते हैं. ऐसे किसी और 2 अपोजिट वाले पॉइंट्स को पकड़ लूं वर्टिकल पे ले जाऊं, तो बाकी 4 हॉरिजॉन्टल पे आ जाते हैं. यानी कि 3 टोटलिटी प्लेन आपको मिलेंगे, एंड दीज 3 प्लेन्स आर कॉल्ड मेरिडियोनल प्लेन. फेसेस समझ में आ गया, मेरिडियोनल प्लेन समझ में आ गया. अब हम समझते हैं कि ऑक्टेटल कॉम्प्लेक्स में हम कैसे ऑब्जर्व करते हैं. तो फॉर एग्जांपल आई हैव अ मेटल आयन to which 3A are bonded and 3B are attached in this fashion. Right? So as I can see, if I join these 3A atoms, they are present on one triangular face. And similarly, if I join these 3B atoms, they will be on the other triangular face at the they'll be at the on the back of the octal complex. And if I observe it from the geometry's point of view, so it means that if you're observing, let me just take two reds. So these are two A atoms which are in the front, and there's one A atom at the top. If I join the three, they're at the triangular base, triangular face. Now, if I talk about the 3B atoms, you can imagine it like this. So what I've done is, I've just flipped the geometry, and let me just flip the molecule and show it from this side. So these two atoms are B, and their third atom, which is B, at the bottom. So they are forming if I join these 3 points, they'll be forming a triangular face. So the same atoms are present on the faces. That's why it's called facial or fact isomer. The other case is the meridional. Now, in this case, if you observe, what I've done is I've placed two A particles on one side and the other A particle on this third side. Okay. So this is how it is. I'm talking about 3A particles, and this is B, and there is one B here, then there is one B below. I think I'm running out of pen. Now, so if I observe these 2A, so these are the 2A atoms or 2A ligands at the front. This is the A ligand which is there in the back. So these 3A are falling on one single plane, that is the horizontal plane, or maybe the XY plane, and it'll be at the meridional plane. Now you would say B is also there. No. So I'm concerned only about A. So these 3A are falling on one single plane. All 3B are not falling on horizontal plane, which I'm observing right now. This is my horizontal, 3A and B, the square plane I'm forming, right? So the 3A are forming, are present on the one horizontal plane, that is the meridional plane. Now, if I observe these 3B atoms, how they are placed, let's see. Now just let's understand this B portion. So in this case, one B's atom is at the vertical top, one B is at the bottom. So these two B atoms are there. This third B atom here, this is A. So we just don't have to look at the A. So these three B atoms are present in the one plane, which is some YZ plane. Or typically, if this I'm taking this as X-axis, this as Y-axis, and this as Z-axis. So they are present on the XZ plane. So all three of them are present in the XZ plane or one of the plane, which is a meridional plane. So this is called meridional isomer or MER isomer. Right. So I think we're still left with the optical isomerism, and we're yet to start transition elements. But we'll catch up for sure. As in these with the syllabus. So we'll discuss the optical isomerism in the next class, and then we'll finish the transition elements. Just go through the cases of the isomerism. It's an important topic in coordination compound. Most of the times, there's very high chance that a question can be asked from this topic. Right? This is it for today. Thank you.